In this module, we're going to explore the digital technologies subject, okay? Specifically, how it's actually being framed in the Australian curriculum and what the expectations are on you as a teacher in order to address the requirements of the digital technologies subject. Now, the first thing we need to understand is the rationale for the subject. And we've looked at the rationale for the learning area of technologies, and we've looked at the rationale for design and technology. Now, these are both a little bit clearer than digital technologies. Of course, digital technologies, being a brand new subject, does need to make its own space and establish its own rationale for being within the curriculum. And actually establishing a new subject, and this is the first subject to be introduced into the curriculum since geography in the 60s, is a difficult and complicated process. So let's look at the rationale as to why digital technologies is having a space within the well-acknowledged crowded curriculum, particularly in our primary years. So the main aspect, of course, is that the world has changed. The world has changed very significantly from the 60s and from the 40s or even the 20s when much of our curriculum was established. So the idea of preparing students for society and for the world of work that currently exists within society is at the core of the digital technology subject. So it's very much got a vocational aspect to it. Now, that doesn't mean that it's only about preparing students for work. It's an important aspect, but certainly it's not the most essential aspect. So we have to be very clear about that. It's not just about learning how to use computers so that you can get a job. That may be a side effect, but it's not the primary goal. So what is the primary goal of digital technologies? Okay. Fundamentally, there are various ways of looking at the world. Now, in science, having an understanding of the scientific method and the content and concepts of science allow us to look at the world differently to how we would look at the world if we'd never learned anything about science. Just the same as for geography or history and the arts and the other curriculum areas. So fundamentally, the rationale of the subject is to provide students with that perspective on the world, because without that perspective, they will be able to less engage with the world as it is today. So there are a few other aspects though. One is that in order to operate in the world of today and to just do basic fundamental social aspects such as communicate with each other, to an increasing extent find a partner and engage with that in terms of a social environment is very much linked in now with our social presence and our understanding of digital technologies. Our ability to engage with recreation. More and more recreation now involves the use of digital technologies. You've got your mobile phones and tablet devices, but also computer games and other aspects. And then, of course, there's the whole social media processes whereby we maintain our contacts with our friends and our families and develop relationships through social media. Now, we can just teach students how to use such technologies, and that would certainly be an aspect of ICT as a general capability. We'll talk about that in a moment. But that really doesn't empower them to take control of how these technologies are managing their lives. To really understand the technologies, and if these technologies are so important in our lives, then that understanding is fundamental. How Facebook works and how it manages a social presence is a very complex process. And having an understanding of that, how the data is stored and shared and how you can then manage that data and sharing by understanding those processes is a very important aspect of today's society. So fundamentally, the rationale is providing that perspective on the world and the confidence and skills and capabilities to actually manage that themselves rather than relying upon others who develop software and other solutions to manage it for them. Okay, so that's our rationale for digital technologies. And of course, the rationale for why it's set in the curriculum is that it takes a long time to develop that worldview. And also, we need to understand that we don't prepare students, and we shouldn't just prepare students, for life after school. Students' lives are occurring while at school. Okay? Students don't start their lives when they reach 18 or 19. They're living their lives now. So it's not just about preparing them for the future, but it's about preparing them to engage with their current practices and their current lives. And as we all know, students are very much intertwined with digital technologies in all aspects of their lives, and that needs to be incorporated into digital technologies education as well, particularly when we sequence when to introduce new concepts. Because if students are already using those concepts as part of their life, then we need to make sure that we can prepare them for that, not just for some abstract time in the future when they become adults. So within this, we have a set of aims. Okay, first is to be able to design, manage, evaluate sustainable and innovative digital solutions to meet and redefine current and future needs. So the key aspect here is that they are actually creating innovative digital solutions. So it's a practical subject. It's not just about theory. It's not just about learning how to work safely on the internet or knowing about how computer programs work, etc. It's about making your own, or students making their own. And then we frame all of this using the thinking process called computational thinking. And next week we're going to spend the entire session talking about computational thinking and what that actually involves. Because that's probably where, it's what will distinguish those of you that simply learn how to do this subject to those that really understand the subject and can engage with it at a high level. Most of you will be able to teach students how to do the various activities that you're seeing in your assessment tasks and incorporate those into your lessons, etc. But actually taking your students to the point whereby they're thinking computationally and they're developing this worldview of digital technologies and being able to modify that world based upon their understanding of digital technologies, that's where the power of the subject will be. And that's what you should be aiming to try to achieve. Now, it's a hard task. I don't expect you all to achieve it during this course. It's something that may take many years to develop, particularly as we don't have a lot of resources and other support mechanisms to assist you with this just at the moment. But a lot of effort is now being put into schools to prepare teachers to do the same as what you're doing now, and you'll certainly be able to tap into that when you get into schools. Of course, it'll take about 4 or 5 years at least before we start seeing real changes to the classroom across the whole nation based upon digital technologies. So there will be the understanding of computational thinking. We've got our key concepts of abstraction, data collection, representation, and interpretation, and we'll talk about those in greater detail next week. Next aim is to confidently use digital systems efficiently and effectively to automate the transformation of data into information and to creatively communicate ideas in a range of settings. Now, a lot of complicated words in there, but fundamentally it's about managing information. Now, it's not just about making posters and spreadsheets and things of that nature. We can go into a lot more detail about actually how information is communicated in the world, how we can create new information, how we can share that information, how sometimes information gets lost, and how digital technologies can be incorporated in all of those processes to improve things. So that's probably the area of greatest weakness at the moment in the curriculum. Not so much in what it says to do, but in terms of how it's framed and for teachers to understand what's possible with information and information systems. Certainly, there's a lot of focus on the programming aspects of the curriculum, but there's a lot of support for teaching of programming. There's not as much support for the teaching of information systems. And that will be something that will be developed over the next few years to hopefully come up to the same standard as the level of support we have for teaching of programming. A couple of other aims: to apply protocols and legal practices that support safe, ethical, and respectful communications and collaboration with known and unknown audiences. So this is really working appropriately in a digital age. And there'll be a number of controversial areas of this that you can engage your students with. Of course, there's the issues of when and where it's appropriate to download different material, when it's appropriate to download and share songs, for example, or movies, or software. And then this whole aspect of copyright. When can you put a picture onto your web page, and when do you need to acknowledge that, or when do you need to pay for that? And there's a whole range of aspects there that students need to learn about. Even though in practice we may break some of those personally, we need to make sure that students are learning about what society expects, or at least the legal aspects of society expect, in terms of protocols and legal practices. And then, of course, there's the whole issue of safety online, and because that's a major concern for a lot of people that are new to digital technologies, it's an area that we need to ensure is addressed during the course, because it's something that can come back to impact upon you personally as a teacher. If you, in your enthusiasm to use new technologies with your students and to engage with new approaches, particularly around social media and social presences on the internet, you may inadvertently contravene some of your school or state policies, or even some legal policies and legal laws. That could open you up to considerable trouble if you don't take those into consideration when you plan your lessons and how you manage risks. Just as we have risk in a science laboratory, we have risks when we engage with online activities, for example. Now, it doesn't mean we don't engage with them. It simply means we need to consider those risks and, where appropriate, place in practice some mitigating processes to ensure that those risks are as low as possible. Now, there's always going to be some minor risks that are possible. Doesn't mean you don't ever do something because there's a potential for something bad to happen. But just as in a science laboratory or a sporting activity or an art room or any other learning activity that may involve a potential risk, you need to be aware of those risks and take some action to mitigate those. And finally, there is the aim to apply systems thinking to monitor, analyze, predict, and shape the interactions with and between information systems and the impact of these systems on individual societies, economies, and environments. So this is really about thinking about digital technologies and how they impact the world, and that perspective that I've been talking about. So trying to see the world as systems and the interactions between various systems. So you don't just see a computer as a computer, you see it as a system within a larger system, and even having smaller systems within it. So the basic system of the computer and your peripherals, such as your mice, your monitor, printers, etc., that forms a system at one level. Below that, you've got systems relating to how information is stored on the computer, to hard disks, or to the internet, or to the RAM and ROM chips, and all those smaller systems. And then below that, you've even got electronic systems with logic gates and digital processing components that you may incorporate into your teaching if you wish to go to that level. But then going the other way, your computer sits within a larger system. The human being using the computer is part then of the system, and the environment around them, such as their ergonomics of their seating, their lighting, the actual workplace itself, whether or not it's a mobile system or set in a cubicle somewhere, that forms a larger system. And then beyond that, you've got that working within even larger systems, such as a school system or a classroom. And that then, of course, fits in with larger systems beyond that, leading into our society. So system thinking is an important aspect, and we'll talk a little bit more about that as we go through. So that's the rationale and aims. As with design and technology, there is two strands with digital technologies. One is the knowledge and understanding, and the other is the processes and production skills. So knowledge and understanding is really the theory, and the processes and production skills are the practical application of that theory to develop solutions to problems. So we have our little diagram that tries to represent that. In the main, it's not particularly important, these particular representations. Of course, there's underlying structures that are more significant, and we'll talk about those in a second. But fundamentally, just as with all subjects in our curriculum, we have knowledge and understanding, and we have processes and production skills. You do need to know those, because they may be on your quizzes. Okay, the relationship between those two strands is basically we use the theory and our understanding of various aspects of digital systems to develop applied problem solving. Now, so within that knowledge and understanding, we've got two main aspects: understanding of digital systems. Okay, so students understanding that their immediate systems are made up of hardware, such as the computer, the software that runs on the computer, the networks that allow communication between computers or digital devices. And students will slowly come to an understanding of that as they go through their 11 years of digital technologies education. And so they get to understand the various physical bits and software parts and communication processes, but then there's also how we actually use the data that's managed by those systems. So how data is actually stored on a hard disk or a USB stick, or how it's stored on the internet, how images are stored on a computer as data, or sound. That's an important aspect of understanding the world from a digital technologies perspective. So a photo is very different on a computer to a photo that exists when it's printed out on a hard copy. How it's actually stored is significant because we can store it, for example, at different file sizes, where we can use various processes to reduce those file sizes, to make the photo take up less space on our computer. And there's a whole range of different ways of doing that. We have different protocols such as the JPEG protocol or PNP, or PNP. There's a whole range of different ways of encoding that photo. And they involve generally losing some data or reducing the amount of data used to represent that photo. So when a photo is taken, it's what's known as RAW, where it uses as much data as possible to capture all the detail of the photo. It's then quite a large file size. But then we use software to take out the information that we don't need to record. Of course, for example, there may be sections of the photo that are similar, like the sky. So we can store that by simply recording the general shape of the sky, and that the majority of the sky then is of a particular color and hue and so forth. So that can be a lot less data to store that than to store each individual pixel or each little dot in a photo, and the color and hue and all the rest that might be stored about that particular dot. So there's a whole lot of what are known as compression processes to reduce down images. And that's important to know. Of course, you may, without that knowledge, think that, okay, I can reduce my photo down, and then at a later time I can increase the size of it again and restore it back to its original detail. But that's not possible, because there's information that is lost when that's reduced. Sometimes it is possible, but in the main, there is information lost when that's done. And by saving the format or resizing it many, many times, more and more data is lost, and artifacts then creep in that create errors in the representation of the image. So they're all things that are important to understand if you're working a lot with images. Similar things occur with movies, digital movies, and with music. The MP3 standard has been around for a long time, but most musicians know that recording songs as MP3s loses a lot of the detail and nuances of the song, particularly at the higher and lower sound bands. And as recordings are made multiple times, more and more errors and data is lost, and the song degrades. Even the fact that data stored on physical devices such as CDs, or USB sticks, and that slowly over time they degrade and errors creep in. So many people still think that data stored on a CD will last forever, but it doesn't. Generally it's got about a 20-year lifespan, and that can be reduced by how often it's used and recorded over, etc. So there's lots of things that having an understanding of how the technologies work allow you to look at the world differently. Okay, moving on. So digital technologies, processes and production skills. So just like with design and technology, this is a process by which students go through to create new solutions or innovations. So we start off with collecting, managing and analyzing data. So instead of just doing research into existing problems and aspects of the materials and so forth, here we generally start with a focus on the data. Okay, because almost all of our digital technology problems will involve some manipulation of data. So how we're going to collect that data, how we're going to manage the collection of that data, how we're going to save it, check that it's correct, go through all of those processes, and then how we're going to analyze it and look at the properties of that data and so forth becomes an important aspect. Then we define the problem and design a solution to that problem. Okay, and in years F to 2, that's what we focus on, and going to years 3 to 10, we develop into defining problems, designing and implementing and evaluating solutions that have been developed by students and evaluating how well existing information systems meet different needs. So in Foundation to Year 2, we're really just focusing on defining and designing solutions, not so much on building them. Years 3 to 10, we incorporate the full design cycle. So a little bit different to design and technology in that respect, where in design technology we start from foundation to do the full cycle. In digital technologies, from foundation to year 2, you can just focus on defining the problem and designing digital solutions without going through the whole implementation and evaluation processes. Similarly, with communicating ideas and information, from foundation to years 4, that's the process that we focus on. And then in years 5 to 6, we expand that to managing, creating and communicating ideas and information. So foundation to years 4, it's just the communication of the ideas and information. But as we go up through the primary years, we need to think more and more about how to manage that information flow and also about how to create new elements of information. So maybe creating a new digital image or a new set of data from a sensor, for example, like a light sensor that might be on a one of our robotic kits measuring different light intensities. And that flowing through as data into our computer system, we can then use that information in different ways. And then in years 7 to 10, we move into working collaboratively. So working in groups on tasks and creating interactive solutions. So solutions that we can actually engage with. So it's not just static solutions like a spreadsheet, but an actual information system, maybe with a software front end that allows you to choose from different bits of information, maybe selecting various sets and then having different processes occur on that information. Okay, so this involves creating and communicating information, especially online, for example, by creating websites and interacting safely using appropriate technical and social protocols. So that's where we bring in some of those other learning aims that we want to achieve during digital technologies. And throughout all of that, they'll be being critical and creative and using systems design and computational thinking. So again, we get to mention computational thinking, where we're going to use a whole range of different approaches, but as we're going to be talking about that in detail next week, we'll leave it at that for now. But within all of this, there are a number of key concepts. These are probably the core of the curriculum, of the subject. Okay, these 5 key concepts. Now the first is abstraction. Now really this represents all of the computational thinking aspects, or the main aspects of computational thinking. So it's how we abstract elements of the real world to represent in a computer. Of course, we can't represent everything about the real world in a computer program or using an information system, because that would be then as large as the real world or the real universe. So we have to actually simplify things. We have to make them abstract. So they can represent elements of the real world, but they don't represent every element of the real world. So for example, a flight booking system to book airline tickets will have some elements that you capture in terms of data about the person's name and their age and maybe their seating preference and their food preferences. Okay, so that's abstracting information about that person. It doesn't include all the information that's possible to collect about that person, because that would be way too much and it'd be unnecessary. So in order to solve our problem, we select just that bit of information that we do need for the solution of the problem, and then we relate that to other aspects like information about the planes and about where they're flying, and about maybe some simple aspects of the weather system. So we abstract the weather down to, okay, is it raining or not raining, or the amount of wind that's flowing and what direction the wind's flowing. Okay, we could collect huge amounts of information about the weather, okay, down to each individual atom in the sky, but that's way too much detail. So we abstract that down to what we just need. So that's an important concept though for students to get, and it's a difficult one because often we see the world in very different ways and we see the world as a very, very complex system. Abstraction simplifies the world into simple systems that we can then manipulate and change if we're representing them digitally, and take control of those systems. Next big key component is data collection, data representation, and data interpretation. So this generally is our information systems. Okay, how we can actually collect information or data, how we can represent that in various ways, as text, as images, as sound, as video, a whole range of different ways we can show that data, and then how we can interpret that data, how we can see patterns and context for that data in different approaches. And we'll talk more about that a bit later, particularly next week when we explore those concepts. Next key element is specification, algorithms, and implementation. This is really the programming. Okay, taking algorithms, which is a sequence of steps or ways we go about approaching something or doing something, and representing those via a computer program. So it's really providing a set of instructions to a computer for it to do something. Next, we have digital systems. This is where students need to understand the hardware, the software, and the networks, including the internet, and how those things work. And finally, we have the interactions. How people interact with computers, how they interact with the data, how they interact with the processes involved on computers, and how these things, how computers and digital solutions may impact upon future environments, but also how they can empower us to do things. So this is really how we perceive the use of digital technologies, how we can use them safely, how we can interact with things more easily, make them more user-friendly and easy to use, and things of that nature. So those 5 elements, abstraction, information systems, programming, computer systems, and interactions and impacts, which we often summarize as human-computer interaction, or HCI. Those 5 elements are what the core of digital technologies is about in terms of the content of what's taught. Remember though, that's not necessarily the aim of the subject. The aim is to provide students with that worldview, okay, that perspective on the world through their understanding of these 5 elements. So this is what's taught, but our aim for teaching these things is not so that they can learn how to program or learn how to create an information system or learn about what the components of a computer are. These provide the context for the learning about and our understanding of the world from the perspective of digital technologies and computational thinking and the other aspects and systems thinking, etc. So that's a very key distinction. Okay? You're going to learn about how to do these little individual aspects and the content of what you teach, but that's not the aim of why you're teaching it. Okay. So again, the text there goes through and explains those different elements in a bit more detail. You can read through that. So, how do we structure all of this so that students can learn it? So lots of people have got together and come up with this as a way of going about teaching all of these different concepts. And this is known as curriculum. So the first is we've got knowledge and understanding and process and production skills. So remember, our knowledge and understanding is summarized as those first two, digital systems and representation of data. So the first bit, well, actually we'll save this till we get into more detail in a moment when we unpack these. But as you can see, there's a general progression from foundation through to year 8. Okay, I've left off the year 9 and 10 material. So that students will progressively develop greater and greater understanding as they progress through their courses of study. I know as teachers you'll focus in on just your year level and so forth, but you need to understand the context of what students will have learnt before and what they need to be prepared to know so that they can move into the next levels. Okay, so let's have a look at a couple of bands and see what the expectations are. So at the very youngest years, okay, from foundation to year 2, students will be doing things such as using robotic toys to navigate a map. Many of you would have seen the B-bots and things like that. Using tools such as data loggers or the Lego robotic kits to record data. You can do that by connecting, say, a temperature sensor or a sound sensor, and maybe all the students clapping and seeing that recorded and then presented as a graph of the different sound levels on the computer screen. Okay, so exploring the basics of how digital technologies work, how we can collect data, or say we can collect information about sound, turn that into numbers, okay, turn those numbers into zeros and ones if we're teaching about binary, and then how that can be then used later, okay, so we can store that then on a computer, and then we can use it later to then turn into graphs, and we can use those graphs to then interpret what the sound was occurring when we were doing our clapping. So that simple process is an example of how students would come to understand how digital technologies can work in the world. Because once you start thinking from that perspective, then you say, okay, what other ways can we collect information, say from sound, that we can then capture using a digital device and then use that information. So we might capture, for example, students' voices and see if there's any differences between their voices that we can interpret in terms of the patterns. So we could record each student's voice, look at how they actually say different words, and see if there are differences between students. Some are going to be louder, some are going to be softer, some might emphasize different parts of a word, so those parts will be represented differently when they're presented as information on a graph or so forth. So the whole idea is to explore how information is stored as data and how we're going to manipulate and use that data in creative and interesting ways. We also look at concepts of abstractions, or start looking at those concepts, and of algorithms and things of that nature. So let's have a look at some of the examples. Okay, so first concept to explore is identifying, use and explore digital systems, the hardware, software, etc. So here they could look at things such as the robotic toys, such as the B-bots, to doing dance movements, constructing various models of digital systems they can use in role plays. So they could do a role play of how an email is transmitted, and try to explain how email goes from their computer to another computer, and role play that by being the various signals going across the internet. Okay, so it's a whole range of different things. They can explore how to use digital systems for downloading and storing information, okay, how to download pictures and put them into a document and save and retrieve data. Okay, but we need to be careful it doesn't just devolve down into just learning about what they should know in relation to ICT as a general capability. Okay, we're doing this from a perspective of understanding the world in terms of computer systems and digital systems. It's not just learning a whole series of skills and capabilities. It's getting students to see the world differently by their understanding of these things. So let's look at a couple of others. Follow, describe, and present a sequence of steps and decisions needed to solve a simple problem. Okay, so lots of simple activities you can do here. Programming a digital TV recorder or DVD recorder or tape recorder, if you've still got those, to record a TV show. Generally involves a series of steps that are programmed into the computer in terms of the time to start the recording, the time to stop the recording, which channel to record, etc. So there's lots of fun activities you can do here where students pretend to be robots or other devices and perform a whole series of steps in a sequence. Okay, let's have a look at some of the other year levels. So in year 3 and 4, okay, define simple problems and describe and follow a sequence of steps and decisions. So same as what we just talked about. But you'll see here they're a little bit more complex. In particular now they're using drawings and pictures to show that sequence. Maybe making a simple game and explaining how others can follow those steps. And in this case, they have to include decisions. So if you remember back to our workshop, we had the selection commands or if-then commands. So if the sound is above a certain amount, then do something. So simple little decisions that are made by the software based upon some input or something changing. Okay, so implementing simple digital solutions as visual programs with algorithms involving branching. Okay, here again we're talking about those branching decisions and implementing those. Here suggesting using some flowcharts or storyboards to show the processes involved, etc. Okay, moving up in the years. Okay, acquiring, storing and validating different types of data and using a range of commonly available software to interpret and visualize data. So here we can use basic things such as graphs and spreadsheets and so forth, but progressively as they go up the years, they'll start using information systems and what is known as query languages. So many of you are familiar with searching using tools such as Google search, but that always brings back a whole set of responses. Okay, often thousands of web pages that you can go and look at. The idea of query languages is to bring back just a single response. Okay, so to specify exactly what is wanted in the query so that it returns just that exact thing that you want to search for. And as you get into understanding query languages, particularly in the upper years, that becomes an important aspect of information systems. Of course, when you want to use that information in an automatic way, you don't want to receive a whole lot of information coming back. You want to get back just a single piece of information. Say, if I want to know a particular student's grade, I don't want to see a list of grades for all students at the university. Okay, I would want it narrowed down to just the students in this course, and then I might want it narrowed down to just a specific student based maybe on their student number. And then I want it narrowed down to just the grade for a particular assessment task so that I get back just a single number. Of course, I might want to then use that result from that query to, say, subtract that from another query or another number. So getting a whole lot of responses doesn't allow me to do that. But if I know I'm going to get just a single response, then I can have that occur automatically to then perform that calculation and then be able to use that in an automated way in a computer program, for example. Okay, so there's lots of different examples there of different learning outcomes. The key thing to remember is that the STEM part, the actual, here the example is design a user interface for a digital system, generating and considering alternative designs. That's the learning outcome that needs to be achieved. The elaboration points are examples of how that can be achieved. You don't need to do all of the elaboration points, and indeed you don't need to do any of them if you come up with your own way of achieving the actual learning outcome. But these are examples to assist you in understanding what's involved with achieving that learning outcome. So you may do it by designing a user interface using different design tools for a game. That would be one approach to doing it. Another approach would be exploring different features of user interfaces to allow people from different cultures to access information using various languages. Okay, that would be a different approach to achieving that learning outcome. And remember, that learning outcome has to be achieved over the 2 years of their course of study. So ideally, of course, you would have some chance to achieve that every year, but there may be some learning outcomes that you decide will be done in 1 year and others in other years. Or they may build upon various things. So that's part of the individual unit planning that teachers will do in their own courses and what you'll do for your final assessment task. Okay, so there are the various learning outcomes and elaborations that are defined in the curriculum. Remembering though, it's only the STEM part that's mandatory. The elaborations are there to assist you in coming up with ideas of how to do that. And over time, there will be more and more resources released that will assist you in doing these. So essentially, there'll be learning packages that will be available. So when you come to think, okay, I need to incorporate how to do this particular learning outcome, and it involves using some binary data, then I'll go and get some learning resources and lesson plans and so forth that will assist me in achieving that. Unfortunately, they aren't developed fully yet. We're in a process at the moment of developing those nationally, and we've done a couple of dozen for trial at the moment, and they're being trialled in schools, but there's not a lot available just yet. I'll present you some of those next week when we talk about computational thinking, but at the moment you're in a little bit of a bind. Of course, you do need to come up with many of these things yourself. So I do take that into consideration when I mark your work and so forth. I understand that you don't have a full knowledge about all the ways of going about teaching these things. But do your best, use the elaborations to assist you. And while it's probably a little bit premature to talk about the your lesson planning processes, so forth, just yet, how you actually integrate all of these into design tasks and learning activities is probably the key aspect. Generally, you won't try to address these learning outcomes individually. You'll incorporate them with other learning outcomes, and they should naturally form into projects and learning activities. So while they're presented here as a whole lot of elaborations that don't seem to really fit in with the other elaborations very effectively, a large part of what we'll talk about in the later stage of this course will be how you'll take these various individual learning elaborations and combine them into learning activities. Design challenges. Okay, we do that a lot and quite easily with the with the design and technology subject, and you're probably already starting to see how they can all fit together into design challenges. Digital technologies is a little bit different to that, but essentially, or certainly the way I teach it in this course, is for you to follow a similar process whereby you create design challenges that can incorporate the achievement of the various learning activities, of the learning outcomes that you're expected to achieve in addressing the digital technologies curriculum. I look forward to our discussion and unpacking some of these in greater detail and addressing any questions you may have or concerns about the particular elements of teaching the digital technologies curriculum. remembering though that you don't yet have a full understanding of computational thinking. That we'll be discussing next week, but for the moment, explore the learning outcomes and the elaborations and come prepared for some interesting questions and discussion at our whole course discussion. Bye for now.